Now in complex analytic function, we'll be looking at Laurent series and we'll be solving few problems on it. Before that, please like, share and subscribe this particular channel and click on bell icon to get a new notification. Let us start now. Now come to Laurent series. Okay. First I'll be showing the definition, then I will be explaining you how to use a Taylor series to form a Laurent series. Okay. Let us start now. The definition is given as nothing but the Laurent series is nothing but let f of z be an analytic function at every point inside and on the boundaries of a ring shape region R and bounded by two concentric circles having a center at A and respectively the radius R1 and R2 such that R1 should be less than R2. Then for all values of z belongs to that particular region R. Okay. Now I'll be explaining you by means of a graphical method. Okay. Now it's nothing but if you circle, consider circles here. We can see that R1 is less than R2 radius, right? Now we have to form a series of an analytic function f of z, right? Now how to do this one is nothing but it is given as f of z is equal to a0 plus a1 z minus a plus a2 z minus a whole square plus so on to a z minus a whole power n plus you consider negative terms also a minus 1 z minus a whole power minus 1 plus a minus 2 z minus a whole power minus 2 plus so on to a minus n z minus a whole power minus n. Now here you can see that they are forming two series, right? We can write in the form of a sum of it. It is given as nothing but summation of n is equal to 0 to infinity a n z minus a whole power n plus summation of n is equal to minus 1 to infinity a of minus n z minus a whole power minus n, which is equal to nothing but we can add these particular two sums, which is equal to nothing but summation from minus infinity to infinity a n z minus a whole power n, right? Now we can see that this particular series is as that determined from what z should be in between R1 and R2, right? Now this particular term is formed for mod z less than R2 and it is known as an analytic part, and this particular part is called as nothing but a principal part, and it is between R1 less than mod z. Okay. Now what is an an? An is nothing but we'll be integrating it. Okay. 1 by 2 pi integration over a closed curve f of z z minus a whole power n plus 1 dz, and n would be from 0 plus or minus 1 plus or minus 2 plus or minus 3 plus or minus 4 and so on. Okay, this is the general definition of a Laurent series. Now to form an analytic function in the form of a series, Laurent series, first you have to know the difference between the Laurent series and Taylor series. Now first if you consider a Laurent series, they will be giving a function f of z and they would be given a region such that it will be in between R1 and R2, right? Then we write this particular function f of z is equal to nothing but summation of n is equal to minus infinity to infinity a n z minus a whole power n, right? And a n is equal to nothing but we're doing an integration 1 by 2 pi integrating over closed curve f of z by z minus a whole power n plus 1 into dz, right? Now as we know in the Laurent series, right, when you're considering two circles centered at an a and they would be covering along in a region R1 and R2 and would be forming in a series in between R1 and R2. Now coming to Taylor series. In Taylor series, what we do is nothing but we're doing the function f of z estimation would be done, right? Only estimation has been done in the case of a Taylor series. We're considering a point, say it is an A point, and we'd be forming in a series for it, and it is defined as f of z is equal to summation from n is equal to 0 to infinity f of n of a by n factorial. Just we are doing the differentiation, right, into z minus a whole power n. right? This is a general series we get directly from a Taylor series. Now when you find the difference between Laurent series and Taylor series, first one you can see that in the Laurent series it is start from minus infinity, but in a Taylor series it's starting from 0. So here it will be from minus infinity to infinity. In Taylor series it's from 0 to infinity, right? And second one, you can see that in the Laurent series we are doing the integration, but in the Taylor series we are doing the differentiation, right? So it's nothing but integrating over in a dz, and Taylor series we are doing the d by dz, right? This is a basic point you have to remember. Now coming to how to find the determinant of a Laurent series. It is from minus infinity to plus infinity, right? So at the maximum we'll be using the Taylor series. Now the basic thing that you have to know is nothing but the first point and second point to use a Taylor series. Is nothing but if mod z less than 1, then the function should be like 1 by 1 minus z. And if mod z should be greater than 1, then the function should be like 1 by 1 minus 1 by z. Okay, we can have something a value can be also kept here. Okay, then we can say that mod z should be greater than e, or so on. Okay, now the Taylor series expansion is given as in the case of mod z less than 1 is equal to nothing but 1 by z plus z square plus z cube, which is equal to nothing but summation of n is equal to 0 to infinity z pi. Now if you consider mod z greater than 1, then we get nothing but f of z is equal to 1 plus 1 by z plus 1 by z square plus 1 by z cube plus all, right? Where it is nothing but summation of n is equal to 0 to infinity 1 by z pi. Now we'll be solving one of the problem for it, for better understanding. Okay, instead of 1, if you have something else, okay, instead of 1 by z, if you have something like a by z, how to do it? Okay, the same method will be doing, but some common terms will be taking in the common. Okay, now come to the question. If you have a Laurent series expansion for f of z is equal to 1 by z minus 3, about the annual region z is equal to 0 is. Okay, for this one what you do is nothing but first step, if you consider this point as an 0 and this is a function, first we're defining for mod z, okay, less than 3. Okay, we have this particular thing 1 by z minus 3, then we have a pole at z is equal to 3. So first we're defining for z less than 3, then we'll be having this particular term, right? Now coming to the other one, here we'll be finding this is 0 point, then we'll be finding for mod z greater than 3. Okay, then we'll be getting for outer regions, right? Now when you add both of them, we get nothing but only this particular point 0, and we'll be getting whole of the nothing but a whole of the Laurent series, right? So we have to find for mod z less than 3 and mod z greater than 3. So let us start for it. Now come to the Laurent series, the same function f of z is equal to 1 by z minus 3. So we can say that there is a simple pole at z is equal to 3. So what we do is nothing but first find the value of mod z less than 3 by using a Taylor series, and you will be adding with a mod z greater than 3 using a Taylor series. Then we get nothing but a Laurent series of an f of z. So coming to the first one, we'll find the value of a mod z less than 3, and the function is given as f of z is equal to 1 by z minus 3, right? So as we have seen just now that it should be in the form of 1 by 1 minus z for mod z less than 1. So when you're converting this one, get nothing but 1 by, if you consider minus 3 common, then you get 1 minus z by 3, right? So we can write this particular expansion as nothing but f of z is equal to minus 1 by 3 into 1 plus z by 3 plus z by 3 whole square plus so on, we get it, right? So it is nothing but summation, we can do it, minus 1 by 3 summation of n is equal to 0 to infinity z by 3 whole power n. Right. Now come to the second one. It is given as mod z greater than 3, and the function is given as f of z, which is equal to 1 by z minus 3. Right. But you have seen just now that it should be in the form of 1 by z. Right. For the second one. So we have to convert this particular function as nothing but, if you consider z common, then we get 1 by z into 1 minus 3 by z. So we can expand this particular function. F of z is equal to 1 by z into 1 plus 3 by z plus 3 by z square plus so on we get it. So when you summate it, okay, it will be in a summation of 1 by z into summation of n is equal to 0 to infinity 3 by z whole power n. Right. If you consider z inside the summation, then we get f of z is equal to summation of n is equal to 0 to infinity 3 power n by z power n plus 1. Right. If you want here also the whole power n plus 1, so what we do is not but plus 1 and minus 1, which is equal to not but get us summation of n is equal to 0 to infinity, it becomes 3 by z whole power n plus 1 into 1 by 3. Right. So we can write this particular term. We got f of z is equal to 1 by 3. We are talking about mod z greater than 3 only still. Okay. Summation of n is equal to 0 to infinity 3 by z whole power n plus 1. Right. So we can write this one as nothing but it is plus 1. So we can start from n is equal to 1. So it becomes 1 by 3 summation of n is equal to 1 to infinity 3 by z whole power. Right. When you take the reverse of this one, then we get nothing but 1 by 3 summation of n is equal to minus infinity to minus 1. Right. Z by 3 whole power n only. Right. So this is an equation. We got it from the second one. And the other one is not my first one. Now we have to find the Laurent series for f of z. So what we do is nothing but add 1 and 2. We are adding 1 and 2 equations. Then we get f of z is equal to the first one as the first term. It is given as minus 1 by 3 summation of n is equal to 0 to infinity z by 3 whole power n plus come the second term, it is 1 by 3 summation of n is equal to, it is summation, right? We can write from minus 1 to minus infinity also, right? Z by 3 whole power n. Now see here, we got a Laurent series. It will be from minus infinity to plus infinity, right? So we got it. It is from plus infinity to minus infinity, or minus infinity to plus infinity. We got a Laurent series. Okay. Now come in just note points of the Laurent series. The first one is Laurent series works for isolated singular point z is equal to a. Okay. For this one, we have just solved a problem for it, that f of z is equal to 1 by z minus 3. So we can say that there is a simple pole at z is equal to 3, right? So we got a simple pole at z is equal to 3, right? When you substitute here f of 3, then we get nothing but minus 1 by 3 summation of n is equal to 0 to infinity. It becomes 3 by 3 z bar n plus 1 by 3 summation n is equal to minus 1 2 minus infinity 3 by 3 whole power n. So this one becomes 1, this one also 1, right? Again you'll be adding from 0 to infinity, right? So it becomes 1 plus 1 plus so on until infinity. So it becomes nothing but infinity. Again here also we'll be adding from minus 1 to minus infinity. So it becomes 1 plus 1 plus 1 plus on until infinity, right? So it becomes infinity only. So when you add it, it becomes minus 1 by 3 into infinity plus 1 by 3 into infinity, which is equal to nothing but we can cancel both of them, which is equal to 0. So we can say that nothing but Laurent series works for isolated singular point z is equal to e. Now come to the next one. Nothing but Laurent series can exactly say the number of poles of an order n. For this one, if you consider an example, like the Laurent series expansion of z is equal to sin z by z cube about the annual region z less than 0. We can see that there are 3 poles, right? So we can say that it's in a pole of order 3. But exactly it is a 3 or not, we'll be finding out by using a Laurent series. Okay. For sin z, we know the Taylor series, which is equal to nothing but z minus z cube by 3 factorial plus z power 5 by 5 factorial plus so on we get it, right? So we'll be finding for f of z, which is equal to sin z by z cube. So the series will be just multiplying the series with 1 by z cube. Then we get 1 by z cube into z minus z cube by 3 factorial plus z power 5 by 5 factorial plus so on we get it, right? So which is equal to nothing, it becomes 1 by z square minus 1 by 3 factorial plus z square by 5 factorial plus so on we get it, right? So we can say that there is only 2 poles. Okay, so we got pole of order 2. Okay, so by using a Laurent series we can exactly say number of poles of an order n. Now coming to the next one, a minus 1 coefficient is called as an residue of a function as z is equal to e. For this one you have to know about the residue of a function. Okay, now coming to the next one, we can use a Taylor series to find the Laurent series. The same thing we have done, right?